of perfectly inelastic collisions, okay? And here we have two objects. Let's choose a color different from both. So we have object 1 and object 2 of mass m1 and m2. They may not be the same masses. They might be the same masses, whatever. They could be anything, m1 and m2. And in this particular case, they happen to be traveling towards each other. So they're going to collide head on. Okay, so this has an initial velocity v1 initial. This has a velocity to the left. It's going to be a negative velocity, v2 initial. And we've shown the positive x direction over here. Then the collision happens. And after collision, because this is a perfectly inelastic case, the two objects get enmeshed and move together as one combined mass of m1 plus m2. No mass is lost. Okay, so no part of it breaks away. And it moves with one given velocity, some final velocity. So my final momentum is this total mass moving with this total velocity. Total n times v. Right? So this is my final momentum, and it must equal the initial momentum, which has two parts, the momentum m1 v1 initial from here, plus momentum m2 v2 initial from here. So this becomes my equation from the conservation of linear momentum. Right? So this has how many variables? 1, 2, 4 masses, 2 for masses, sorry, let's go back, and 3 different velocities. So total of 5 variables. If you know any 4, the 5th one might be asked for, and you can solve this equation for 1 variable. Yeah? In the case of elastic collisions, typically the case becomes more complicated. We have 2 types of conservations. Here on top, you see the same type of equation as before, except in the final case, our 2 masses are not joined together, so they may have separate velocities, v1f and v2f. Yeah, they are not joined. So remember, in the elastic case, we have the collision, and after collision, our objects may go their own ways. They are not entangled. And the second conservation that happens in the elastic case is the kinetic energy is conserved. That means the initial kinetic energy for the system must equal the final kinetic energy for the system. So that's half mv squared, remember? It's half m1 v1 initial squared plus half m2 v2 initial squared equals the kinetic energy of the first mass, half m1 v1 final squared plus half m2 v2 final squared. This is my total final kinetic energy equals my total initial kinetic energy. So we have 2 equations, these 2, equation 1 and 2, and you need to solve them simultaneously. You still have the same, now you have 6 variables, right? Because you have 2 different velocities at the end. 2 masses and 4 velocities, 2 initially and 2 finally. So you have 6 variables, out of which you could have any 2 unknown, because you have 2 equations, so you should be able to solve for 2 variables. Yeah? So these become simultaneous equations. They also have squared terms, so these typically tend to be slightly longer problems. Let's look at an example of a collision problem. Okay, so a block of mass m1, this one, 1.6 kg, moving to the right with a speed of 4 meters per second on a frictionless horizontal track, collides with a spring, okay, and the value of k for the spring is given. So initially, I have this mass moving with this velocity, right? They've given you the picture, so you don't need to draw it. We know the spring constant. It collides with the spring attached to a second block of mass m2, which is 2.1 kg. So we know the second mass. That is moving to the left with a speed of negative 2.5 meters per second. So they told you that this is going to be a negative velocity because it's to the left. After the instant that the mass m1 compresses the spring by delta x, the speed of mass m1 is reduced to 3 meters per second. Okay, so it slows down from 4 to 3 in the same direction. Part A, determine the magnitude and direction of the velocity of m2 at the instant m1 is traveling at 3 meters per second. Okay, so it's a frictionless system. We're going to assume that total energy is conserved. Also, our linear momentum is conserved because in any kind of system it is conserved. And what happens after collision? Do we know anything after collision? It does not say that they join together. So you cannot assume that it's perfectly inelastic, okay? So you need to write out the total momentum before collision, and then the total momentum at the final position when this block is moving with a velocity of 3 meters per second to the right, yeah? Because that's the instant that we are interested in. So final doesn't mean it's final resting position. Final is just the position or the velocity that you are interested in. So here they are before collision. In this case, the momentum is easy. You need to multiply this value m1 with this v1 initial, add it to m2 plus m2 times negative 2.5, right, which is v2 initial. That should give you your total initial momentum, and you need to set it equal to the total final momentum, which is going to be m1 v1 final. So this momentum of this one we already know. That leaves just the momentum of this, m2 v2 final, and we know m2, it's given in the problem. So just v2 final is my only variable that I need to find out. So just from the equation of linear momentum, I should be able to solve for v2 final. We need to find its velocity and we need to find its direction. Yeah, the magnitude and direction of the velocity. The magnitude is going to be the number, which we will calculate. The velocity, we will know from the sign, whether that comes out to be positive or negative. Okay, so on the next page, we'll see how we did it. And I want you to have a go with having learned my strategy, pause the video here, and try to work it out. Part B, by what distance x is the spring compressed at the instant m1 is traveling at 3 meters per second squared? So this is about thinking about the total energy of the system. So we need to think about what is my total kinetic energy here. Let us assume and set our potential energy reference as 0, right in line with where the masses are. So the potential energy is never in play. The height is not changing. We have 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared, right? The spring is not compressed, not elongated, so it stores no energy at the start. That's all my total energy at the start. This must be equal to the final total energy, which is the kinetic energy m1 v1 final squared, plus the energy stored in the spring, because the spring gets compressed, so that's 1/2 kx squared, plus m2 v2 final squared. So you're going to need the result from the first part to plug in to find the kinetic energy of this, to plug that in, so that only the x, that's the amount of compression in the spring from its normal resting length, is unknown. Same as that delta x. Yeah? So you can solve for it using the total energy conservation. Okay, so here are the results. For part 1, this is our linear momentum conservation. We solve for V2F, since we figured out that that was the only unknown, right? And that's what we need to find out. Then you substitute in the values, plug all that into your calculator, and you should get negative 1.74 meters per second. That means V2F is traveling to the left because it's a negative sign. So we know the direction and we know the magnitude. For the second part, and it doesn't say part 2 here, but maybe we can write that in. For the second part, let's just write that in. So this is part 2, or part B. We're going to set the total energy initially equal to the total energy finally. There's no potential energy in place, so here's the sum of all the initial kinetic energies and the spring potential energy, which is 0. Sum of final kinetic energies and the spring potential energy. You need to solve for this x, right? And when you do that, you're going to see that it comes out to be 0.173. Okay?